Good morning, good afternoon, and good evening. Welcome to the session on civil and scientific applications. The session will include 2 invited talks and the panel. My name is Jolanta Kuśmierczyk-Michulec, and together with Georgios Haralabous, we will co-moderate this session. Georgios, please introduce our first invited speaker.
Thank you. Our first invited speaker is Dr. Oçal Nekmioglu. Dr. Nekmioglu graduated from Istanbul Technical University in 1997 as a geophysical engineer and started his career as seismic analyst in oil exploration. During 2001-2008, he worked as seismic, hydroacoustic, and infrasonic analyst at the IDC, and afterwards joined the Kandili Observatory and Earthquake Research Institute, COERI, in Istanbul, Turkey. While continuing his CTBTO-related work at COERI, he also pursued his academic studies and obtained his PhD degree in 2014 in geophysics on tsunami hazard in Turkey and surroundings. He is currently the manager of the Turkish National Data Center at COERI and assistant manager of the COERI Regional Earthquake and Tsunami Monitoring Center, providing tsunami warning services to Eastern Mediterranean, Aegean, and Black Sea. Since 2012, he has been acting as the tsunami national contact for Turkey with respect to UNESCO Intergovernmental Oceanographic Commission, and as a CTBTO PrepCom Working Group B task leader on testing, provisional operations, and performance assessment. It is my pleasure to present Oçal. The stage is yours.
Yes. Thank you very much, Yorgo, and thank you very much, Jolanta. My impression was that you're going to be presenting my video recording, but I can do it online if that's the case.
No, that is true. The video is coming up.
Okay, thank you very much.
The stage is still yours.
Yes.
Apologies, just give us 1 minute to solve the technical issue. We'll be back. Dear Otal, may I kindly ask you to go live, because we have an unexpected technical issue here, but please, by all means, continue, and please unmute yourself.
Okay, Yorgo, I'll do my best. You know, this is called Murphy's Law, and as someone responsible in tsunami early warning system, these things happen at the time that you don't want it.
We tried so many times before, but it's okay, please.
Yeah. So I guess you should be able to see now my screen and presentation on full mode. Okay, thank you very much. Good afternoon, Vienna, and good time of the day for the participants of SNT 2021 from all around the world. It's an honor and privilege for me to be able to address to you on the linkage among sustainable development, disaster risk reduction, and CTBT verification regime. As Yorgo kindly introduced, my name is Özal Necmoğlu. I'm the NDC manager in Turkey. I'm also the Tsunami National Contact. And there were several presentations and posters presented during this week related to the topic that we are interested in. But I guess my roles in the CTBT framework and both national and intergovernmental responsibilities related to tsunami early warning and mitigation under the UNESCO Intergovernmental Oceanographic Commission puts me in a unique position to elaborate further on this topic. However, before I start, I really would like to use this opportunity to express our deep appreciation for Dr. Lasina Zerbo's remarkable leadership as the Executive Secretary of the CTBTO PrepCom, including the promotion of the entry into force, universalization of the treaty, strengthening of the verification regime, as well as the enhancement of the civil and scientific use of IMS data. We're also grateful for his strong support to our NDC and its staff, ranging from our active participation at Working Group B meetings to the capacity building programs conducted by the CTBTO and participation in CTBTO's flagship scientific event, Science and Technology Conference, where we all meet today. Last but not least, I also would like to express my special thanks to my colleagues, Yolanta, Yorgo, and Mario from BTS for providing me material that improves my presentation. Based on all the presentations and discussions that have taken place during the SNT 21 so far, you should be impressed by now on the capabilities of the IMS and the significant progress achieved during the last decade. Almost 90% of the network foreseen by the treaty has been certified, and the verification regime has already demonstrated its capabilities and readiness towards entering into force at many occasions, thanks to approximately $2.5 billion investment and 25 years of professional commitment and successful collaboration between member states and the PTS. The treaty has not entered into force yet, and very few of us might have an insight on when this could happen. In the meantime, IMS data is being used extensively for many civil and scientific applications, such as detection of earthquakes and near real-time tsunami warnings, volcanic eruptions, and further contributing to the scientific studies in climate change, meteorology, marine and ocean life, and atmospheric events detectable by the IMS. But this wasn't the case always. As Jorgo mentioned, I was a staff member of the IDC at the time of the catastrophic Sumatra earthquake and tsunami, which cost around 250,000 lives in 2004. In fact, I was responsible for the analysis of the main shock, which took me 3 full days to associate all seismic phases. I do clearly remember heavy criticism on the restricted data distribution policy of the CTBTO at that time. The criticism was not justified, perhaps into consideration the limitations put by the treaty, but at that time, the collaborative framework we enjoy today between the broad scientific community and the CTBTO did simply not exist. The Sumatra event was a milestone for the PTS to not only make its data available to tsunami warning centers through an agreement with UNESCO, which my country enjoys also, but also in terms of opening its doors to the non-CTBT scientific world. Even though it was preceded by a large-scale eruption of Sarichev Peak, Kuril Islands in 2009, the second milestone in this regard was the volcanic eruption in Iceland in 2010, in my point of view, which had a large impact on the aviation industry. The controlled airspace of many European countries was closed, resulting in what at that time was the largest air traffic shutdown since the Second World War. The closures caused millions of passengers to be stranded not only in Europe, but across the world. With large parts of European airspace closed to air traffic, many more countries were affected as flights to, from, and over Europe were cancelled. This event resulted in the improvement of the volcanic ash advisory through better monitoring and understanding of the prognosis of such events, and also opened the way for the establishment of a volcanic information system through a European Commission funded research project. And then came the Tohoku 11 March 2011 earthquake and tsunami and resulting failure of the Fukushima nuclear power plant. Just one day after the event, the IMS started detecting radioactive particles emitted by the damaged Fukushima power plant. The radioactive cloud was then detected gradually by IMS stations as it traveled first to Russia and then United States before dispersing across the northern hemisphere and later around the entire globe. While the levels detected were far below those that would impact human health, the IMS demonstrated its ability to track radiation from nuclear accidents quickly and accurately. Furthermore, dispersion was predicted correctly using atmospheric transport modeling, the method which the travel path of a given radionuclide is calculated either forwards or backwards, making use of meteorological data. On the basis of this data, CTBTO member states were able to provide reliable information to concerned populations. The Fukushima accident also led to intensified cooperation between the CTBTO and other relevant international organizations such as IAEA, WHO, and WMO. Another example, wildfires in the Chernobyl exclusion zone, which broke out last year in April and lasted for several weeks, resulted in the resuspension of cesium-137 into the atmosphere and observed through the IMS network. In addition to volcano eruptions and earthquakes, a range of meteorological events emit infrasound, such as severe storm systems, air and ocean waves, meteorites entering the atmosphere, and auroras. What is considered a disturbance or noise in the data when monitoring treaty compliance is of relevance to the climate science community. IMS data is important for the research on the atmosphere, severe storm systems, mountain waves, etc., phenomena that can undergo significant changes as a consequence of climate change, as already stated in 2007 by Professor Kronk-Kolb. In a near real-time operational setting, it is even argued that monitoring the infrasonic waves that precede tornadoes could produce earlier and accurate tornado warnings. The IMS network allows also, for example, a better understanding of submarine volcano dynamics through seismic and hydroacoustic investigations. Among many examples presented to you during this week, a very recent publication on the identification of a new whale population in the Indian Ocean through the IMS hydroacoustic network is especially noteworthy, I believe. This is only one example of many related to the science we need for the ocean we want, as advocated by the United Nations Decade of Ocean Science for Sustainable Development, which started this year. All what I've presented as examples do fit United Nations Sustainable Development Goals of climate action, life on water, life on earth, peace, justice, and strong institutions and partnerships for the goals. As a strong institution of peace, supported by the partnership of member states, the CTBTO is de facto serving these goals in a unique manner. The Sendai Framework for Disaster Risk Reduction 2015-2030, as part of the broader sustainability vision, aims to substantially increase the availability of and access to multi-hazard early warning systems and disaster risk information and assessment to people by 2030, so that a significant reduction in the global disaster mortality and affected people could be achieved. I have borrowed the next 10 slides from my talk at the Science and Technology 2019, focusing more on the target G of the Sendai Disaster Risk Reduction Framework. But let's have a closer look to the natural disasters from a wider angle, as presented by the UNISDR in its Economic Losses, Poverty and Disasters 1998-2017 report. As an average, approximately 85% of natural disasters are climate-related, where the remaining 15% is dominated by the earthquakes, volcanoes, tsunamis, and landslides. Among the climate-related natural disasters, around 40% are due to floods followed by storms by around 30%. Earthquakes, however, are responsible for more than 50% of the deaths from natural disasters, followed by storms and floods constituting together around 30%. Around half of the economic losses are due to storms, this followed by earthquakes and floods with an equal share of approximately 25%. To name a few catastrophic events with high economic impact, Tohoku earthquake and tsunami in 2011 resulted in around 230 billion US dollar, and the cost of Katrina, Rita, and Wilma hurricanes in 2005 was around 200 billion US dollars. The cost of Sichuan earthquake in 2008 was close to 100 billion US dollars. During 1998-2017, disaster-hit countries reported direct economic losses valued at 3 trillion US dollars, of which climate-related disaster caused more than 75 of the total. Overall, reported losses from extreme weather events rose by 250% between the last two 20-year periods. In absolute monetary terms, over the last 20 years, the USA recorded the biggest losses of around $1 trillion US dollars, reflecting high asset values. China, by comparison, suffered a higher number of disasters than the USA, but lower total losses, which amounts to around 500 billion US dollars. Such losses are only part of the story, since the majority of disaster reports do not contain economic data. The World Bank has calculated the real cost of the global economy is a staggering around 500 billion US dollars per annum, with disasters pushing more than 25 million people into poverty every year. It's critical to note that absolute losses mask the relatively greater burden of disasters on the poor. When economic costs are expressed as an average percentage of gross domestic product, this becomes clearer. Only one high-income country, Puerto Rico, ranked among the top 10 in terms of percentage of GDP losses over the past 20 years. Apart from upper-middle-income Cuba, the other worst-hit nations were all lower-income countries, led by Haiti. So what do we talk when we talk about natural disaster risk reduction in the context of sustainable development? It's obvious that we talk about global inequality. Inequality is even greater than available losses data suggests because of systematic underreporting by low-income countries. While high-income countries reported losses from more than 50% of disasters between 1998 and 2017, low-income countries only reported from 13% of them. No losses data are therefore available for nearly 87% of disasters in low-income countries. A similar divergence in record keeping is evident geographically. Oceania recorded losses for more than 50% of climate-related disasters during the same period, but in Africa, the figure is just 14%. Thus, the economic statistics are the tip of the iceberg as far as low-income countries are concerned. For disasters since 2000, in low-income countries, an average of 130 people died per million living in disaster-affected areas, compared to just 18 in high-income countries. That means people exposed to natural hazards in the poorest nations were more than 7 times more likely to die than equivalent populations in the richest nations. A similar pattern of deep inequality is revealed by georeference ratios of people affected but not killed by disasters. while the largest absolute numbers of people affected by disasters lived in upper middle income countries. By far the highest number per 100 inhabitants lived in low income countries. Again, the contrast is sharpest between low income countries and high income countries. People in the poorest countries were on average 6 times more likely to be injured, to lose their home, be displaced or evacuated, or require emergency assistance than people in rich nations. All of this happening in a world with more than 2 billion people lacking safe water at home and basic sanitary services. More than 800 million people do not have basic drinking services, and around 900 million people defecate in the open. More than 250 million people spend more than 30 minutes per round trip to collect water. I'm not even referring to the added complications due to the COVID-19 pandemic that we are experiencing today. On this slide, you see 4 maps showing the states that has signed but not ratified the treaty at the top left, states that has not signed the treaty at the top right, nuclear weapon states at the bottom left, an informed risk index at the bottom right, developed by a multi-stakeholder forum scientifically led by the Joint Research Center of European Commission, which presents a convolution of hazard, exposure, vulnerability, and lack of coping capacity of a given country. You will notice that excluding a few among nuclear weapon states, it's obvious that almost all developing countries with no interest in nuclear proliferation are associated with a higher risk in terms of hazard exposure, vulnerability, and lack of coping capacity. The CTBT framework ensures a sustainable platform for natural disaster risk reduction in developing countries with no interest in nuclear proliferation, while developing and maintaining global experience related to CTBT verification. Through its capacity building programs, both in terms of human and institutional capacity, the framework especially assists developing countries in their effort of better analyzing natural hazards, which poses risk to them. What is noise from the CTBT perspective is a signal for many of us, and studying the noise in all technologies of the verification regime in detail assures a better classification of a signal relevant to the CTBT. The framework allows also opportunities of NDC to NDC interaction, and for example, efforts by the Austrian NDC in this regard have always been highly regarded. Another added and critical value of the CTBT framework is the fact that it's opening horizons for data fusion using data from different technologies, which wouldn't be possible for many of the national authorities if data from CTBTO would have not been available. You have had many examples on data fusion during this week, but allow me to focus on one from our NDC in Turkey, which was presented during the e-poster session on Wednesday by my colleague, Dr. Korhan Umut Şemin. To name a few, CTBTO data allowed us to study bolide entry and impact in the eastern Black Sea coast of Turkey, fireworks factory explosion in Sakarya in western Turkey, and Beirut harbor explosion, all during last year, using infrasound data from CTBTO and local, regional, and CTBTO seismic data. To conclude, as stated wisely in the preamble of the United Nations Charter, the principal determination of the humanities to save succeeding generations from the surge of the war, to reaffirm faith in fundamental human rights, in the dignity and the worth of the human person, in the equal rights of man and woman, and of nations large and small, rich and poor, to establish conditions under which justice and respect for the obligations arising from treaties and other sources of international law can be maintained, and to promote social progress and better standards of life in larger freedom. CTBT serves the need for continued systematic and progressive efforts to reduce nuclear weapons globally, with the ultimate goal of eliminating those weapons, and it plays a critical role in achieving a general and complete disarmament under strict and effective international control. Noting that approximately $2.5 billion has been invested in the CTBT verification regime so far, the recognition and promotion of the civil and scientific use of its data, ranging from tsunami warning to volcano monitoring, from climate change to better understanding of the ocean processes and marine life, is critical to maintain member state and public interest and investment in the state-of-art system, even beyond the entry into force of the CTBT, also to preserve national CTBT verification capacity in a sustainable manner. Thank you.
Thank you very much. We will take questions during the panel discussion because unfortunately we don't have time now for questions. So please submit your question to the chat and we will address later during the panel. Let's move to the next invited talk. Our invited speaker is Dr. Zainabu Mindaudu Suri, the IDC director. Dr. Zainabu Mindaudu Suri, the IDC director, has been the special advisor to the President of the Republic of Niger in the nuclear field since 2012. She has served as the chair of the High Authority for Atomic Energy of Niger since 2014 and as the vice chairperson of Working Group B of the Preparatory Commission for the Comprehensive Nuclear Test Ban Treaty since 2016. She has been a lecturer in electronics and detectors for master's degree students at the Faculty of Sciences and Techniques at Abdul Moumouni University of Niamey, Niger, Niamey since 2012. Dr. Suri holds a PhD in applied physics from the University of Paris and advanced studies diploma in optical and microwave communications from the University of Limoges, France, and an engineering degree in electronics instrumentation from the University Farhat Abbas Satif, Algeria. Previously, Suri headed the Department of Nuclear Physics and Chemistry of Radioisotopes Institute and the Nuclear Instrumentation and Computer Sciences Laboratory of the Nuclear Physics and Chemistry Department of Radioisotopes Institute. Dr. Zainabu, floor is yours.
Thank you.
I'll share the presentation.
Okay. Yes. Is left power Q. Okay, good. So can I start? So good afternoon. I am here today to talk about civil and scientific applications of IMS data, mainly the Virtual Data Exploitation Center, VDEC. The outline of my presentation is as follows. I will start with a brief introduction, and then we will discuss civil application, followed by scientific ones, in which we will see the VDEC in more details. And the presentation will end with a summary. So, yes, the main purpose of the CTBT verification regime is to verify the compliance with the treaty effectively. So the IMS data is really, they are really a tremendous asset. The treaty explicitly states that member states can benefit from the application of this technology for peaceful purposes. Later on, in the paragraph 10 of the Article 4, it is again stated that this data can be used for scientific purposes. So the PrepCom The PrepCom has defined the users, the category of users. The main users are the one designated by state signatory to monitor the nuclear explosions. And later on, the PrepCom gave authorization for 2 civil applications that are the tsunami warning centers and the radiological and nuclear emergency. Again, the PrepCom later on gave authorization for scientific use of this data, and this led to the access to data by VDEC. So by civil applications, we refer to natural and man-made disasters, which require data to be available in near real time. So data are used for earthquake disasters. And in this image, you can see the event recorded by the system since until 2020. So the Fukushima accident, the Fukushima Daiichi nuclear power plant accident released radioactivity, and in this map, you can see the ATM for the seismic event. That was forwarded by the stations during 4 months, I think, 4 or 2 months, 4 months from starting from the 12th of March 2011. So it covers the northern hemisphere, and this data were very early shared with the International Atomic Energy Agency and the WMO, and 1 year later, the CTBTO became a member of the Interagency Committee on Radiological and Nuclear Emergency. So about the infrasound, observations offer a range of possible civil applications, and there is a well-mastered capability of identifying explosive volcanoes, eruptions that promptly release a large amount of ash into the atmosphere and poses several threats to airplanes. Sorry. It can allow also to detect and locate the meteorite impacts and track the storm. These are a few examples among many others. So for the hydroacoustic part, the data from hydroacoustic data, the data have several potential civil applications as well. Together with seismic applications, seismic data, they form the basis for tsunami early warning. They are frequent underwater earthquake, and many of them are tsunami-genic potential. The CTBTO provides data for tsunami warning centers, national and regional, and they are recognized by the Intergovernmental Oceanographic Commission of UNESCO. So far, 15 tsunami warning centers are receiving data in 14 states. So let's come to the VDEC. VDEC is the Virtual Data Exploitation Center, and it allows the researchers and scientists to use the data after 3-month delay for their scientific application. So the access to VDEC is granted after signing a zero-cost agreement, and the strong relationship between the scientific and technological community helps the CTBTO helps to ensure that no nuclear explosion goes undetected. So it's easy to apply for VDEC. You have a form on the web page that you fill, and when you fill the form, you immediately receive the agreement, confidentiality agreement. This agreement can allow up to three users, but each one must sign a confidentiality agreement. Separate one. So this information are available on the website. So these are some statistics of the number of VDEC projects per technology. And note that yes, around 12% are using more than one technology, but each technology is used in the VDEC project. There are many. So if you heard about this pygmy whale colony that was recently discovered in the Indian Ocean, it was possible by access to IMS hydroacoustic data through through VDEC agreement. So another one, but very tragic example is the Argentina submarine, Ara San Juan. So here you have few examples of the use of hydroacoustic data in VDEC project, and about the radionuclide data, they can be used for to study atmospheric behavior, and it was done to monitor the Fukushima nuclear power accident. So the effects of climate change can be also be followed by the use of beryllium-7 as a tracer for various atmospheric processes. So the most prominent example of scientific applications of IMS data are related to the nuclear test announced by the DPRK. And scientists are investigating characteristics of source depth to enhance 3D monitoring methodologies based on moment tensor analysis or cross correlation. Here, this image is showing various atmospheric phenomena which causes infrasound signals that are noise for 3D monitoring. So this noise can be used for scientific, this noise effects, they are potential that can be used in scientific research for a wide range of investigation. That we put here few examples. So to summarize, we have two main applications, civil applications of IMS data: the tsunami early warning by regional and national tsunami warning centers, international cooperation in case of nuclear or radiological emergencies, and there is also potential for many more applications. About the scientific applications, the strong relationship between scientific and technological community and the CTBTO helps to ensure that the IMS remains at the forefront of technological innovation and that no nuclear explosion goes undetected. Thank you for your attention. I hope I did not took too much time.
Thank you very much. Now I'm afraid we don't have much time for questions.
During the panel.
So yes, so we will address questions during the panel. So now, before start the panel, let's introduce the rest of panelists. And our panelist is Professor Scioli Perez Campos. Professor Scioli Perez Campos has a doctorate from Stanford University and has been a visiting researcher at the California Institute of Technology. She has received student and professional awards, the most recent from the Stanford School of Earth, Energy and Environmental Sciences, for her professional career as an alumnus of that university. She has extensive and active participation on boards of directors of professional societies, both Mexican and international. She is currently a professor at the Institute of Geophysics and a lecturer at the School of Engineering and the Graduate School in Earth Sciences at the National Autonomous University of Mexico. From 2014 to 2021, she was the head of the National Seismological Service of Mexico, dealing with the rapid response to significant earthquakes, informing authorities and the public, participating in town halls at the Mexican Congress, and enthusiastically participating in a variety of outreach activities in Mexico. Welcome to our panel.
I would like to present Dr. Mohamed El Gabri. Dr. Mohamed El Gabri is an associate professor of seismology at the National Research Institute of Astronomy and Geophysics in Egypt. He received his bachelor's, master's, and PhD degree from Mansoura University in Egypt in 2003, 2006, and 2012, respectively. He participated in and coordinated many national and international projects. His research is concerned with mitigating natural hazards in cultural heritage sites and providing the seismological observatory and improving the seismological observations in Africa. In 2018, Dr. El Gabri was elected as a member of the Executive Committee for the African Seismological Commission. Also, he is a member of the Egyptian National Committee for Geodesy and Geophysics. In the CTBT context, he serves as a non-resident expert of the Egyptian Permanent Mission to the CTBTO Preparatory Commission with interest in the IDC progressive commissioning and OSI-related activities.
Our next panelist is Dr. Alex Yezi. She is an NSF Earth Science postdoctoral fellowship at the University of California, Santa Barbara, researching volcano infrasound and seismology. She focuses on constraining the effects of the atmosphere and topography on observed infrasound signals to better understand characteristics of the source at both global and local distances. Alex is particularly interested in quantifying the potential directionality associated with volcanic eruptions and buried chemical explosions and its impact on our ability to monitor and calculate source parameters, including mass flow rate and explosion yield. During her PhD at the University of Alaska Fairbanks, Alex worked closely with the Alaska Volcano Observatory, allowing her to directly apply her graduate research, participate in numerous volcanic eruption responses, and broaden her fieldwork experience. Welcome, Alex.
Our next panelist is Dr. Wenbo Wu. Dr. Wenbo Wu is a postdoc scholar in seismology working at the Seismological Laboratory at the California Institute of Technology. He received his bachelor and master degrees in geophysics from the University of Science and Technology of China in 2008 and 2013. In 2019, he obtained his PhD degree in geophysics from Princeton University. His PhD studies primarily focus on deep earth seismic structures, including the core, lower mantle, and mantle transition zone. He is also interested in numerical simulations of seismic wave propagations in the solid earth and ocean. In 2019, he moved to Caltech and worked as a postdoc scholar. Now he is collaborating with oceanographers to develop a new technology of seismic ocean thermometry. This new method uses the ocean acoustic waves produced by natural earthquakes to monitor large-scale ocean temperature changes. This could help us better understand the role of the oceans in the global climate changes, and we had the pleasure to see his presentations in different meetings. Welcome to this panel.
Dr. Christian Maurer gained a diploma in meteorology in 2004 and in geophysics in 2007. He finished his studies with a doctorate in meteorology in 2012. Christian Maurer worked as a university assistant and project staff at the University of Vienna, Austria, between 2007 and 2012. In 2012, he joined SANC to work on the analysis of the Fukushima accident and on building a quasi-operational demonstrational web-based system for volcanic ash SO2 forecasts. He became a member of the National Data Center of Austria in 2014, where he is responsible for acquiring IDC radionuclide and ATM output data and backtracking suspicious radionuclide measurements. In 2016, he became leader of the so-called Second ATM Challenge in close cooperation with the IDC. It had 17 participants from 10 different countries all over the world. Another challenge followed in 2019-2020, which saw again 16 international participants and created an even larger data pool to be currently evaluated. The main purpose of the exercises is to demonstrate the usefulness of stacked emission data in combination with ensemble ATM for analyzing in the industry-related radioxenon background at IMS stations. Welcome, Christian, in our panel.
Okay. So I think now we are ready to address the first question to our panelists, which is explain briefly your field of expertise and in what type of studies did you use CTBT data. You can use a presentation if you want, or you can verbally respond to the question. Please, the floor is yours.
So maybe we'll start with who is the first one?
Well, if you allow me to start, then
Yes,
I'll
please.
jump in. Okay, let me just share my screen for a quick set of slides to support my talking. So I work at the National Autonomous University of Mexico, and this university is the responsible for the National Seismological Service, which was founded in 1910 and transferred to the university in 1920. The Seismological Service is the official institution in charge of the earthquake monitoring in Mexico. Nowadays, the network consists of 63 broadband stations distributed in the whole country. Additionally, the SSN, or the National Seismological Service, operates one of the hydroacoustic stations of the CTBTO. This station is called HA06 and is located in Socorro Island at the Pacific, about 580 kilometers from the coast and 200 kilometers from the Rivera Fracture Zone, which is a very active region. The HA06 station was installed in 2004 and consists of 3 components located at the south, east, and north of the island. Since it was installed, it has been used to locate 93 events with magnitudes ranging from 4 to 6.4, most of them located at the Rivera Fracture Zone, as noted in these yellow dots. Using this station at the island, the location of the smaller events was possible. The location and the uncertainty was reduced for these events. A similar use is reported by other national seismological centers that use CTBTO stations to complement their networks. The National Seismological Center of Chile reports a similar case. The data of the CTBTO hydroacoustic station and Juan Fernandez Island is now going to be used for tsunami early warning. Going back to the station at Socorro Island, let me tell you that the island is hosts a Navy station, and the Marines are the only inhabitants. They face an important hazard since their active volcano, the Everman volcano, here at the island. Therefore, HA06 components serve to monitor the volcano, and in case an activity associated to it is identified, further analysis and the consequent decisions could be made. Let me summarize by saying that CTBTO has become an essential ingredient in earthquake monitoring for many countries. CTBTO stations either complement their networks or they are even the backbone of the networks.
Thank you very much. So who wants to be the next one to share experience and explain briefly about his or her field of expertise? And
Yolanda, if you're in need of a next one, then please be so kind.
Go ahead, Christian. Yeah, please, by all means, please.
Yeah.
I guess we need to show your slides,
Yeah,
yes?
yes. Mm-hmm.
So it's the one.
Which one?
Now.
Okay, Christian, you are on.
Yeah, so thank you very much. So let me first start with my expertise and background. So my expertise and background is clearly large to mesoscale atmospheric transport modeling with model FlexPart, as it is well known at CTBTO. And my targets are volcanic emissions, as Yolanda already mentioned, but also nuclear releases. And if I say nuclear releases, I really focus on the radioxenons, which more and more gained importance through the last years within or in the frame of the verification regime. And I'm doing numerous projects and studies together with the PTS, so either as a contractor or as kind of scientific support of the Austrian NDC to the PTS. And here I'm showing the titles of two papers. So the paper to the left reports the results of the second so-called ATM challenge. And the paper to the right deals with the added value of ensemble prediction modeling, ensemble prediction modeling with regard to dispersion for CTBTO applications. Well, and I have to state that the work would not exist without IMS data when it comes to the ATM challenges. So they are entirely based on the existence of IMS radioxenon data. And when I have a look at my other work, which is displayed here, yeah, it also relies to roughly 75%, I would say, on IMS data. So you clearly can see that my research interest and focus very likely would be quite different without CTBT and IMS data. So my research is really tailored to questions which are based on IMS data. So if you could go to the next slide, please. Yeah, and I really have to say that I like this data very much because I think there's a uniqueness of CTBTO IMS data, and I, of course, focus on IMS radionuclide data. So what are very important aspects for me? So this is the common high standards for a global network. It's not just a regional or national network, it's really a global network. Then I think, yeah, some simple things, but which really can be a pain if you work with radionuclide data. So you can be sure that daytimes are always in UTC when you work with CTBTO data. I have quite some experience with national data, and there you will have to face the question: is it Central European time? Is it Central European summertime? Is it Eastern European time or Eastern European summertime? Then collection start and stop are always provided by default. And this can be a pain with national data too. I remember one experience where only the midpoint times were provided, but with midpoint times alone, yeah, you do not get far in ATM modeling. Then another very important aspect is that collection times are no longer than 24 hours and do not change substantially at an IMS station. This means data is thus easy to process and yields valuable profiles for ATM evaluation and a solid basis for source characterization. So with national data, you usually face the problem that it has by default sampling periods of 1 week, and only in case something suspicious is recorded, then they are shortening the sampling intervals. And finally, MDC or LDC are also provided by default, and this is also important for ATM evaluation. So then my final slide, please. Yeah, here I would like to answer the question, is my research applicable to data analysis methods of the PTS? And I hope that this will be the case, at least in future, so that ensemble forecasting of the civil radioxenon background at IMS stations will be incorporated operationally. But there are some research questions that need to be addressed on the way forward. So these are: how accurate in terms of time resolution does the emission inventory need to be, taking into account typical transport ranges and typical IMS station sampling times? So this is a very important question. And yeah, we clearly should try to get a solid answer because yeah, it may not be needed, or it's probably not needed to work with 10 minutes or 15 minutes emission time intervals. Then another important question is, are some sources more important than others? Are NPPs, not nuclear power plant emissions, are not as important as medical isotope production facility emissions? I don't think so. What is the effect of unknown or poorly characterized sources? You will often experience the problem that what you predict is too low compared to the actual measurements. Then we have to answer or find an answer to the question, how well performs a multi-input, multi-model ensemble, as was investigated within the ATM challenges, and what is the problem of redundancy? And what was investigated in this other paper I showed was the performance of ECMWF multi-input ensemble prediction system ensemble. And I think there is quite some value in this approach. You find here below related plots of these ensembles. Yeah, and finally, I would like to close with the remark that the ultimate goal, but this is probably very well known to most of you, is discriminating civil radioxenon background from violations of the testband treaty. Because yeah, radioxenons are most likely to emerge from an underground explosion, which was performed by TPRK in the last years. So this is really the critical tracer we have to care about is radioxenon. And with this, I would like to thank you.
Thank you very much, Christian. You covered many questions, so it was very interesting. So now I propose to change the field and move to seismic ocean thermometry. So Venbo, would you like to share your experience and tell us something more?
Sure, I'm very pleased to introduce our work. So can you see the slides?
Yeah, but you need to, there you go.
Okay.
That's it. Thank you.
Okay, yeah. Thank you. Thank you for the nice introduction. And what I want to talk about today is seismic ocean thermometry. Specifically, we are using acoustic or sound waves generated by earthquakes to measure ocean temperature changes. So here I will show how our work is related to CTBTO and why CTBTO data is unique for our study. And at first, I want to briefly introduce the motivation of our study and the idea of seismic ocean thermometry. So why we care about ocean temperatures? Well, a big scientific question or motivation behind there is the global warming crisis, which is related to everybody of us. There is increasing evidence to support that our Earth is getting warmed up. And how this warming evolves in the next decades or centuries is regulated by the ocean, because most of the excess heat in the warming process eventually goes into the ocean. So to better understand the global warming, we need to know how the ocean temperature changes. However, accurately monitor the ocean temperature change globally is very challenging, because our ocean, is huge and poorly instrumented. And what we do here is trying to develop a new and very cheap method called seismic ocean thermometry to look at the ocean temperature changes. The idea is using the ocean sound waves generated by earthquakes to monitor large-scale ocean temperature changes. Our method is based on two key things, basically. At first, submarine earthquakes can produce strong sound waves or acoustic waves in the ocean. And secondly, how fast these sound waves travel in the ocean, they are very sensitive to ocean temperatures. Basically, sound waves travel faster in the warmer ocean, as you can see in the left figure. Based on these two things, what we can do is analyzing how fast these acoustic waves propagate in the ocean. That tells us how fast the ocean temperature changes. It sounds crazy, but actually it works. The right figure here shows our recent published results in which we use the existing seismic data to infer the ocean temperature changes in the northeastern Indian Ocean. And the time we are studying here is from the year of 2005 to 2016. As you can see, there are 3 lines in the right figure. The blue line is our result, and the other 2 orange and green lines show the predictions by 2 popularly used oceanography data product. As you can see, these 3 lines are very nicely consistent with each other. That means our method works. And the below 3 numbers below the figure, they are the linear fitting of these 3 lines, and positive numbers here mean the ocean is getting warmed up. However, our result as blue line is able to provide higher temperature resolutions, and a large number of 0.044 degree per decade from our result means the northeastern Indian Ocean might be warmed up faster than we thought. And so in the previous slide, I demonstrated results from the northeastern Indian Ocean. Our next step is trying to apply our method globally. As you can see, there are many submarine earthquakes occurring globally every year in the left figure. So in the left figure, purple and the yellow dots are earthquakes below the ocean. However, recording these sound waves is not easy because it's quite difficult to install seismometers in the ocean. It's quite nice that CTBTO has built up an excellent hydrophone and T-phase network in the ocean to record these signals. This data is now shared with scientific communities with 0 cost. As shown in the left figure, the circles and squares in this map, they are the CTBTO hydrophones in the Pacific, Indian, and Atlantic Ocean. And now we are trying to use this unique and very high quality data to measure the ocean temperature changes in the past decades. As you can imagine, CTBTO made tremendous efforts to get permissions and spend quite resources to build up this network. However, for our purpose to do a global application, we hope to get an even improved data coverage. As I said, the CTBTO network gives us a very high quality data, but it will be very difficult to build more similar hydrophones for us. But fortunately, we have some new opportunities, and here I just list 2 of them. The first one is the autonomous hydrophones. Different from permanent hydrophones like the CTBTO hydrophones, these hydrophones, they are drifting hydrophones in the ocean and much cheaper. So this map in the middle, it shows us the hydrophones deployed by the Princeton universities and others in the Pacific. Another new technology is called distributed acoustic sensing. This new technology just helps us turn the optical fiber to seismometers or hydrophones. So we could use the existing submarine cables to get a global coverage. And this kind of new technologies would allow us to achieve an improved global coverage. And I think CTBTO would be also interested in these new technologies. And eventually, we can combine these existing CTBTO data and future new deployments to get a better global coverage that helps us monitor global ocean temperature changes much better. So this is what I want to share today, and thanks.
Thank you very much. So now I would like to ask Alex. Alex, could you share with us your experience?
Hold on one second. Okay, can everyone see the screen?
Yes.
Perfect. So as they mentioned before, my name is Alex Yetzi, and I'm currently a postdoc at the University of California, Santa Barbara. But what I'm going to be talking about today is what I worked on as a PhD student up at the University of Alaska Fairbanks, where I collaborated rather closely with the Alaska Volcano Observatory. So I'll be talking very briefly on atmospheric propagation modeling and how we can use that to help aid volcano monitoring using the remote infrasound arrays, such as that of the IMS. So there's a lot of volcanoes globally, and a lot of them are rather remote with little to no local monitoring. So in the bottom left panel, I'm showing the IMS stations with triangles, or the IMS infrasound stations rather, and the red is showing active volcanoes in the last 10,000 years. And the IMS, as well as other regional infrasound arrays, can help detect, locate, and quantify volcanic emissions. And like a couple of other talks this morning have already mentioned, one of the main hazards globally from volcanic eruptions is the ash plume that's in the air. So many of the people in Europe remember the 2010 eruption in Iceland. So on the right-hand side, the top figure is just showing some average daily flight paths, a lot of which go over Alaska, over here, over Iceland, and other volcanic centers. So the need to detect and figure out which volcano is erupting and how much ash and where it's going as near real time as possible is very important for volcano monitoring. But one of the issues with infrasound, at least at long ranges, is that the propagation path is very dependent on the atmospheric conditions. So the wind and temperature structure from the ground surface up to about 140 kilometers in altitude. And these can change rather rapidly and over very short distances. And these atmospheric conditions can either enhance the infrasound propagation in one direction, so with the winds, and also diminish the propagation of infrasound in the opposite direction against the winds. And therefore, this affects the detection capability. So in the bottom right-hand side, I'm showing an example figure from a paper published a couple years ago that spans about 4 days, and the figures are cycling through every 6 hours. So all three panels are showing altitude from 0 to about 140 kilometers on the y-axis, and the wind speed is shown here, the temperature structure over here, and then what is shown on the right-hand panel is what we call the propagation modeling or ray tracing from the source at 0 kilometers range out to the infrasound array here at about 450 kilometers range. And this is from an example eruption of Pavlov volcano in Alaska. And what you can see is that there's very different paths that the infrasound is likely to be propagating in that lower atmosphere, the troposphere, to the middle atmosphere, the stratosphere, and all the way up to the thermosphere at about 120 kilometers. And so it's very important to try to figure out which path the taking. One second. Okay, so what I've been working on is that we have these infrasound arrays such as the IMS, which is really great, but the atmospheric conditions change quite a bit. And so infrasound propagation modeling can complement these array processing at the IMS arrays in order to help situations such as distinguish between changes in the source itself, so whether or not there's more or less ash coming out of the volcano, or if it might be changes due to the propagation path over time. It can also allow for increased accuracy of travel time measurements because infrasound will propagate faster in the lower atmosphere because it doesn't have to go all the way up to the thermosphere and back down. And can help anticipate where acoustic energy is likely or unlikely to be detected in given circumstances. And as well as we want to figure out how much ash or quantify the size of a nuclear explosion. So propagation modeling can help model the expected attenuation of a signal so you can better characterize the amplitude at the source. And while infrasound propagation modeling is nothing new, I bet you about 80% of the presentations this week on infrasound have mentioned some form of propagation modeling. But what we tried to do when I was a PhD student up at the Alaska Volcano Observatory is to actually use propagation modeling as a forecasting tool to be able to help monitor volcanoes. And here we can run forecasts up to about 24 hours in advance, every roughly 6 hours for volcanoes that might be erupting. And so on the right-hand side, we're showing an example of Boguslav volcano here, where we have that lower atmospheric duct to the north, which just goes off into the ocean. And then you can see the colors are showing the travel time where the infrasound is likely to bounce back down on the Earth and be able to be detected. And so these other dots are just showing some of the regional infrasound arrays in Alaska. And I'll note that IS-53 is just off the map up here in Fairbanks. And so as one final quick example of using this in real time is something that we presented at ITW a couple years ago. And so Seismology volcano is about 2,000 kilometers away from the mainland of Alaska, so it's rather remote. And it had just some local seismometers on it and regional infrasound arrays. And so a couple years ago, the seismicity picked up out of nowhere, lots of strong tremor, and we were trying to figure out, is ash being emitted into the air? Like, should we notify someone? Or is it just magma movement below the surface? And so the closest infrasound array was about 250 kilometers away, the ADAC infrasound array. And it's showing that neither the lower atmospheric duct or the middle atmospheric duct existed. An infrasound array is located here where this big red arrow is, and it's called a shadow zone for that thermospheric duct. And so the lack of infrasound detection at this array should not be interpreted as a lack of eruption because the propagation conditions were not great. So we wouldn't necessarily expect to see a signal even if the volcano was erupting. And so that's what I have for you now, and I look forward to further discussions.
Thank you very much. So now let's turn to Mohammed. Mohammed, screen is yours.
Thank you, Lanta, and thanks for all the panelists for very interesting presentation. I will be pouring, I will not be using PowerPoint, so I will be speaking. For my experience, by education, I'm a seismologist. For a long time, I'm working in the National Data Center for Egypt. So my work was always related to using IDC product and IMS data. Fortunately, there is not much relevant event to the treaty. So we don't have a nuclear explosion every day. So it is very important to practice and to use, especially that we are in the testing phase for the IDC progressive now. It's very important to use the data and to check for, I don't want to say problems, but I say challenges and how we can enhance the IDC product and the data. Mainly, I use the data I used it for tomography, for Eastern Mediterranean tomography. Also, we are using it in seismological monitoring in Africa, and it is very important because in Africa we have lack of stations, seismic stations, and IMS provide a very good opportunity to have data in areas where have less, as we have a global coverage for the network. Integrating all of this is very important and very also challenging for us. And this an overview for what I'm doing. Thank you.
Thank you very much. So now we can ask Otar. Otar, we listened to your very nice presentation, but maybe you can add something on, related to your personal experience.
Yeah, thank you. Thank you very much, Yolanta. If you allow me, I have a couple of slides that I can use during this panel discussion. And I'll start from the tsunami early warning point of view at the local regional level. This is a map showing the events for which my institute has sent tsunami warning messages since it's operational, since it became operational in 2012. And the green area is the earthquake monitoring area, and the whole basins, ocean basins, are that areas that we monitor the possible tsunamis. So you can see that various alert categories have been observed, and end users have been notified. That includes the tsunami of Bodrum Coast in 2017, and in October last year, the Samos earthquake and resulting tsunami as a result of the magnitude 7 earthquake. In the heart of the system is actually the earthquake observations. This is a classical traditional tsunami early warning system is based on. In that respect, while many local and regional seismic stations are available, it is an added value to have data from CTBTO most importantly, that the CTBTO's data has its importance in terms of data delivery requirements, data availability requirements, even though at this stage and during its provisional operations, it's probably on a voluntary basis, on a goodwill basis, but at the end of the day, it is still subject to certain performance criteria that puts a different framework to the data that we receive. One other thing is that in our research that I try to present also in my talk, but it's the data that is unique from the PTS is the infrasound data that allows us to work on data fusion, that allows us to work on topics that we wouldn't be working normally because of the lack of the data availability. And these examples, as I tried to summarize in my presentation, was a bolide entry or a fireworks factor explosion or the case of the Beirut harbor explosion. So thank you very much. That's for now. Thank you.
Thank you.
Well, thank you very much. We have a couple of questions from our viewers. One question I think is for Alex. How does the recorded infrasound data related with the ask risk emitted?
Yeah, so that's a really good question, and it's also very hard to answer. So the infrasound data recorded at long ranges, like I mentioned, can be really affected by the propagation conditions. So the signal can either be highly attenuated if it's traveling higher up in the atmosphere. And so figuring out what is happening on the source, at the source, when you're recording infrasound at ranges of 1,000 kilometers away is a very active area of research. And so there's a couple of models that have tried to figure out, to model the source as either a monopole that radiates equally in all directions or a dipole that might have directivity. And then using these assumptions along with the vent radius and maybe the speed at which ash is being emitted to try to relate that to ash plume height. So it's a very active area of research that's ongoing. And I think the best way that we can try to figure out the hazard is to connect with multidisciplinary data. And so we have infrasound, but we also have satellite and seismic and SO2 emissions. And that's kind of the best way to figure out the ash risk by using remote sensing data as well.
Thank you very much. And we have a couple of questions for Venbo. One is, it's a question regarding the stability of the environment, of the weather conditions, as how about the stability in case of storm? That's one question. And the second is very specific. How deep is the sensor below the surface of the ocean of the new technology that you mentioned?
Yeah, for the first question, I think is, yeah, I'm not very knowledgeable to answer that question, and I'm seismologist, and yeah, if anybody in this panel discussion could help, and that would be very helpful. And so I would like to talking about the second one. The second one is the how deep this the sensors, especially the new technologies. And for the CTBTO, the CTBTO hydrophones, they are installed in the SOFA channel, and the depth varied, but basically it's about 1,000 meters below the sea surface. And for the new technologies, first for the cables, the distributed acoustic sensing. For the cables, you know, it's currently the cables they go just at the sea floor. So that's where we can get the data. It means it's the signals we detected, they are at the sea floor, at the bottom of the ocean. And for the drifting hydrophones, the autonomous hydrophones in the ocean, and for such kind of hydrophones, we can adjust them, and we can just tell the hydrophones just park at that specified depth. This depth, it could be from 0 and to up to a few thousand meters. Probably it would be a little bit difficult to get like 10,000 kilometers. That would be very deep. but I think it's reachable. Just some techno. We need more cost to design this sensors. But basically, it's a few thousand meters that range. You can just adjust them, the depth you want.
Okay, thank you very much. So yeah, regarding the stability, of course, when you have drifting platforms or moving platforms, of course, the weather conditions, underwater currents, and so forth, then they affect measurements, and that can play a significant role when you analyze the data. But thankfully, with the hydroacoustic stations, the hydrophone hydroacoustic station, we don't have a major issue with that. So let's see, we have 15 minutes. Yeah, let me go to the other baseline questions that we have for all of you, and they have to do basically with the value of the CTBTO data. I would like you to elaborate a little bit on the issue. What makes that data set from CTBTO unique, and what would you not be able to achieve without the CTBTO data? And as you address these questions, we will be definitely interested to know what are your future plans, any other VDEC requests coming our way from your future projects. We're very happy to hear about that. So any volunteers for that, or shall we continue with Rembo for the future plans? And then since we are talking about hydroacoustics now.
Okay, yeah. It's yeah. I'm pleased to talk about this, and actually there are a few talks. I noticed that a few talks in this year's meeting, they talk about the distributed acoustic sensing, and is it possible in the future, CTBTO can get this technology and install it in the current hydrophones? Because currently the these hydrophones, they are connected with cable. So we have the hydrophones like 50 kilometers away from the island. It's connected by the cables, and in the cables, some fibers probably they are not used. I'm not very sure about that. So they are not. It's just backup. And if this is the case, can we use this technology, to get additional data from the cable? And this is a very interesting topic. And for the current CTBTO hydrophone data, they are very unique for us because currently I would say it's the best global network, hydrophone network, accessible, at least accessible for us, and they are open to scientific communities. So this it's very great. And now we are working on this, and it turns out the data quality is excellent, very excellent for our study. Yeah, we are still working on this, and we hope to get more stations, but we know it's difficult. CTBTO, as I said, made tremendous efforts to build up this network, and adding more hydrophones. Yeah, it's not that easy.
Thank you very much. Thank you very much. These are very interesting ideas for the next generation of hydroacoustic stations, and definitely many speakers and experts that pointed in this direction during this S&T conference, and we will take them into serious consideration. Oczal, would you like to share your thoughts about the future?
Yeah, sure. Thank you. I'm gonna share one more slide. And I thank Wembo for that inspiring remarks, because what I want to point out is that 25 years ago, we all had a different means and understanding of data sharing. The number of observation points around the globe was a lot less than what is available today. Open data policy today is something that everyone is advocating. It's a world of science and technology driven, And we have had many examples of the new technologies in all fields that supports the verification regime. So one thing is, for instance, the smart cables for observing the global ocean, and that was presented by Dr. Ho. I believe not exactly this map, but he had another map on his presentation yesterday. So looking at the IMS network and knowing that the treaty does not allow adding new stations, and then at the same time witnessing and acknowledging the scientific and technological process, the progress in the observations, and more data being available. The question is that in 10, 15, 20 years time, would we need the CTBTO data? That is the question I'd like to bring up. Because if the CTBTO framework, in terms of number of and geolocation point of observation, stay rigid and static, which what the treaty proposes, and at the same time the world moves into a direction where the number of observations increases, just like the smart cable approach here, new technologies, and how would that interaction would work? I think this is one question that I have in my mind for the future outlook. And this is also the reason that I think there is a strong need, the coupling between the civil and scientific use of IMS data, because it also will ensure the sustainability of the CTBTO itself. Unless this cooperation is becoming stronger and stronger, assume that the CTBT will enter into force one day. The added value of the network might be limited only the data availability requirements and not per technology. I know it's speculative, but I think this is something that we have to keep in mind and think about it. Thank you.
Thank you very much.
Thank you very much, Rochal. That's yeah, indeed something you have to keep in mind. One comment on my side, I don't know how fast can we fast forward into the future, but you know, the physics of the ocean and acoustics and propagation dictates certain locations and position in the water column of the sensors that we have in our network, and everything else, everything new will be measured against that performance. So in that respect, yes, we can have hybrid systems and we can couple new and old technologies, but for the time being, I think we are on solid ground with what we have. So yes, we safeguard what we have now, but we look towards the future for the new technologies. Absolutely, yes. Please.
So, Alex, could you maybe share your opinion on this topic from your perspective? What makes the CTBTO data unique?
No problem. So one of the things that makes the CTBTO data unique is for all of the data streams is that we have this really global network that was designed to be able to detect an event anywhere on the globe at any given time. And so I think that has been incredible. But the IMS, or having the IMS, I think has really pushed forward the field of infrasound. And that's probably because of they have really high standards for data quality, equipment. So it's kind of increased research on things like optimal array design. So having the ability to detect broadband signals by having array geometries with a smaller inner circle and as well as an outer one. Things like high quality sensors that are required by the IMS stations, which will help both regional monitoring, temporary deployments. So everything benefits from what the IMS has been doing to push infrasound forward. And I think looking forward to the future, one of the main issues that we have is that we have propagation modeling codes that we can use, but one of the bigger unknowns is the actual atmospheric dynamics itself and the uncertainties associated with that. So moving forward, I think that is going to be a large area of research that's going to be ongoing, including things like internal waves, gravity waves, uncertainties in the atmospheric data itself, And I've heard a bit of talk this week on potentially using LiDAR sensors in order to get atmospheric profiles, and that would allow us to better quantify the sources using infrasound data.
Thank you very much. I would like now to ask Shiori.
Thank you. Oops, sorry. I think one of the advantages of having the CTBTO data available is that it's high quality data and you can trust on the high availability as well. I think this data set has pushed forward a lot of research on detection techniques, also discrimination techniques to visualize better or detect better those events that are not earthquakes and could be explosions. I think a nice example is what happened at the Beirut explosion, that lots of the data from the CTBTO were used, not only seismic, but also infrasound. I think the whole CTBTO data set has driven the research community in many directions that are innovative, such as using machine learning and artificial intelligence. And we have witnessed this week lots of those advances. And so the question is how we're going to push forward these topics for the future. And it's interesting what Okal mentioned, that regarding the fixed structure of CTBTO and how flexible it could be in the future to allow new technologies. And however, having something that it's is as stable as CTBTO is also useful as a baseline and keeping that in context.
Thank you very much.
Thank you very much. Also, we have a question or a comment from Paul Richards for you. Do you agree that we will still need a good bulletin of seismicity, and then member states can pursue special studies of interesting events? So again, it's on your future projections. Any comment on your side?
Yeah, I think. Oh, sorry. Yeah.
Yeah, that was from for Ochal, but then absolutely.
No, sorry. I missed. Yeah, please.
Yeah, absolutely.
Yeah.
That was for Ochal first. Yes, thank you.
Okay, thank you very much. I don't know if you can feel how much I start sweating. You know, it was like in my PhD dissertation, receiving a question from Dr. Paul Richards is always something that is exciting. I'm gonna try to give a short answer. I think there is a need for a discussion on what the product is for. What the CTBTO product, Seismic Bulletin, is for, and whether it has to compete with the International Seismological Center's bulletins. So if this is a controversial topic, and I think we're coming closer to a time where we need to have a detailed discussion on this, because this issue is also closely linked with what is called so-called the product quality. So how would you define the product quality for something that is designed for the CTBT monitoring? And when you start comparing it with a global seismological bulletin produced and published 2 years after by the International Seismological Center. So I'm not trying to be political here. It's a difficult question, but I believe it's important to define what is expected, clearly define and understand what is expected from the CTBTO product. So we need that bulletin, the product, in high quality, but in a way that satisfies the verification regime needs. Probably nothing more than that. The rest is subject to scientific work that is probably not going to be covered by the operational service of the verification regime. I hope I was able to give an answer. Thank you.
Well, thank you very much. That's a topic that requires further discussion, of course. Sorry for interrupting, Sioli. I think you wanted to comment on that. Please, by all means.
No, sorry. Thank you. And I think I agree with Ocal's comment at the end. Yeah, thanks.
But if you want to add something, you are welcome.
Yeah, I will add that the bulletin is a base for what it's for its own purpose. So maintaining it can give it continuity. But at the same time, I agree with Ocal that the research community has other objectives and it needs more products.
Okay. We have one.
May I comment here?
But by all means.
Yes, please.
Yeah.
Go ahead.
I totally agree by what Ocal has shown, and I would like to emphasize more on the criticality of the situation here, how we can balance between the treaty requirements and the member state requirements and the needs for scientific community. We have an opportunity here that we are having a very high quality data with homogeneous distribution all over the globe. I think Wimbo has highlighted how it is complicated to have permission, even permissions to install such sensors. It is very challenging. And we need to keep this, because having the politician, which is their interest is disarmament, in the loop is giving us privileges, and we need to invest these privileges. And I think here we need to think about two things, about the definition of event, because we have a definition for the event in the treaty context, and we have a definition for the event and for us as a scientist. Maybe my event is Ocal noise sometime. It's very different. So and I believe here it's the place where the NDCs can play a bigger role. Maybe the BTS rule is mandated by the treaty provision and the PREPCOM mandates, but NDCs can play bigger roles, having regional cooperation and even international cooperation between the NDCs could enhance this. There is no constraints for NDCs for the data usage and how they are using the data and how they are exchanging. And I believe if we will have a space or a room for development in the context of using IMS and IDC, it will be in the cooperation between NDCs in future.
Thank you.
Thank you very much. I would like to make one final comment, because many of our viewers are asking where can they find the VDEC information that was projected in one of the slides. But if you go to our main website, ctbto.org, www.ctbto.org, there it's extremely easy to navigate through and find the VDEC information. You can contact any of us anytime, and we can give you that information.
Yeah, and I'm the focal point of contact for VDEC.
So I think with that, we come to our concluding comments. We thank you all for a wonderful presentation, excellent discussion, and we certainly hope that we see you soon in person in the near future for another such interesting discussion.
So see you next time in Vienna, I hope.
Thank you very much.
See you. Bye-bye.
All the best. All the best.
Bye.
Bye-bye.
Everyone.
Bye-bye.
Thank you. Bye.